So now, here we have machine components design. We are still under the design of shaft. Now this part will be based on the failure of shaft due to bending moment only. So when we refer to bending moment or the bending of shaft, first we have to take a look at the simple bending equation. Okay, so we have strength relationship. The strength relationship consists of the M, which is the bending moment, and the I is the moment of inertia. The I is the moment of inertia, and sigma here is the bending stress, and Y is the vertical distance from the neutral axis. So M, bending moment in Newton meter. And I would be the moment of inertia or the second moment of area in meter to the power of 4. And sigma is the bending stress due to bending moment, which is in Newton per meter square. And Y would be the vertical distance from the neutral axis. Okay, so we refer to this for the variation of sigma, the bending stress, with respect to the Y. So what it indicates here is, okay, when we are looking for maximum bend stress, then the Y should be maximum. That means the vertical distance from the neutral axis should be maximum as well. Then when we refer to the minimum bending stress, we will have Y minimum. Then for stiffness relationship, we have the M over I is equals to E over R, where E is the Young's modulus and R is the radius of curvature. So M is bending moment, I is the moment of inertia, E is the elastic modulus or the modulus of elasticity in Newton per meter square. And R would be the radius of curvature. So now, based on the bending stress, sigma is equals to my over I, where m is the bending moment, y is the vertical distance, and I is the moment of inertia. So for a circular cross-section bar, that means a shaft. So you can see, okay, this is circular cross-section. This is your y-axis and x-axis. So this I here is different from the torsion. The torsion, we have polar moment of inertia, which is J, and it is the second moment of area about the z-axis. That's for polar moment of inertia. But for the moment of inertia or the second moment of area, for bending, we will take x or y. So we assume that the shaft or the bar here will bend about the x-axis or the y-axis, and it is not rotating about z. Rotating, then you will have to consider turning moment. What we are looking here is bending moment. So the moment of inertia about the x or the y is the same, which is given as pi d4 over 64. But for polar moment of inertia is 32. Polar moment of inertia, remember, is about z-axis. That is only applicable when we are looking at torsion or turning moment. Now, for a hollow circular shaft, then you will have pi d4 minus d4 over 64, where this d here we refer to the external diameter of the shaft, and the lowercase letter d here refers to the internal diameter of the shaft. Now, for the bending moment, we have to refer to cases of how the shaft is being supported, whether it's cantilever or it is simply supported, and what type of load, okay, is acting on the shaft. Because usually the shaft is mounted with gear, pulleys, or flywheels, which you have weight acting on top or on the shaft that causes the shaft to bend. So we have, or it is very important that we have to know the condition of the shaft of how it is being supported, cantilever or simply support. So the bending moment M here will varies. The maximum bending moment here will be different for different cases or different conditions. So we have standard conditions that I will list down here. Okay, so the first one is the cantilever, which you have the shaft being fixed at one end and then free at the other. So let's say in case you have a flywheel or a pulley placed on the shaft at this end here. So it actually exerts a load or a wave W, which is also a force at the end of the shaft or the beam. So it causes maximum bending at this point, which is shown with my pointer here. So you have the maximum bending here. So the most important thing here is when we design of shaft, it's very important for us to know what is the maximum bending moment for the case. So for cantilever, the maximum bending moment is given as W, that is the load, multiplied by the length of the shaft. So that means your maximum bending will be here. Just like you are taking bending moment at this point here, okay, at the laser pointer, you will have W times L. So the shaft or the beam will bend in this manner. So the maximum bending that takes place will be at this point. And it is given as W, that is the force in Newton, multiplied by the length, which is in meter or in millimeter. So that the next case here is the uniformly distributed load. This one usually refers to the self-weight of the shaft. So it is given as Newton per meter. And the maximum bending moment also occurs at this fixed end here. Okay, so the maximum bending moment in this case is given by omega L squared over 2, where omega is the uniformly distributed load, which is usually the weight of the shaft itself. So next would be the simply supported beam or shaft, where you have central load, or let's say you have a point load acting at the center. Just like, for example, you have a gear placed at the middle of the shaft. So that also will cause bending due to the weight of the gear or the pulley itself. It will cause bending in this manner, as is shown in this diagram here. So the maximum bending occurs at the midpoint, okay, or at the point at which the force is acting. So the maximum bending moment for this case is WL over 4. W would be the point load or the weight of the component that is placed on the shaft times the length, the total length of the shaft divided by 4. Then the next, when you have point loads acting not at the center, which is at any point along the shaft. So let's say, for example, now you have a pulley placed here. So the pulley also causes weight. So this weight will act as a point load acting at the point on the shaft. So the maximum bending in this case can be determined or can be found by taking WA, which is this length here from the left-hand support, multiplied by B, which is the length from the right-hand support, and then divided by its total length of the shaft. Then the next case would be the simply supported uniformly distributed load. Okay, I need to remind you again, the uniformly distributed load here usually refers to the self-weight of the shaft. And the maximum bending will again occurs at the center, and it is given by omega L squared over 8, where omega is the uniformly distributed load, the self-weight of the shaft, which is Newton per meter. It is different from the W that we have, which is the point load. The force here is measured in Newton, and this is measured in Newton per meter. That means it is based on the meter length of the shaft. So let's say, for example, you have 0.1 meter. So if you want to find the total load, then you have to take omega, which is in Newton per meter, multiplied by 0.1 meter. So the Newton per meter with the meter will cancel off, so you get the Newton. So the maximum bending moment is given as omega L squared over 8. Okay, so these are the standard cases we will be facing in the design of shaft. Most of the time we have uniform shaft in our case, but then if you go for further, when you go further in depth, you will be facing with shaft of varying sections. Okay, so this is for the first explanation on the shaft failure based on bending moment. So I will see you in the next slide. Thank you. Stay safe. Hi again. So this part, we will deal with problem solving. Problem solving due to the failure of shaft because of bending moment. Okay. So take a look at the question. This is supposed to be example 6. Okay. A pair of wheels of a railway wagon carries a load of 50 kilonewton on each axle box, acting at a distance of 100 millimeter outside the wheel base. The gauge length or the gauge length of the rail is 1.4 meter. So you can consider this as the total length, and this would be the distance at which the support are, and this would be your point load. Now find the diameter of the axle or the shaft between the wheels. If the stress is not to exceed, so this would be the bending stress, 100 megapascal. So I have drawn the diagram here with the wheels. Each of it has a reaction because it's touching the ground. So you have 50 kilonewton and 50 kilonewton on the as supports on the wheel, okay? As supports on the wheel, and at this point you have load of 50 and 50, which is given in the question. So which is 0.1 meter from one end and 0.1 meter from the right hand end. So the distance in between should be 1.4. So the total length should be 1.5 meter. Okay. So this will be the maximum this will be the bending moment diagram, not the maximum. Maximum bending is here. So even though it's shown as -5 by magnitude, but value-wise, compare 0 and 5. So 5 will be maximum. You just omit the sign. Unless if you got positive and negative sign, then only you start comparing. Okay, so our maximum bending based on the bending moment diagram which I have drawn, the maximum bending moment will be 5 Newton meter. So how to find the 5 Newton meter, or how to draw the bending moment diagram? So what you have to do is you have to consider bending moment from one point to another. Okay, and you have to start from either end. So you have to start from, if you start from, okay, the left hand end, then you have to cover all whatever that is towards the right hand side. Okay, so that means you are looking only at point A alone. So when you look at point A alone, which you are covering this whole section here, when you look at point A alone, so the bending moment will be 50 is the force times the distance. The distance will be 0 because you are considering you're placing a plane here. So you are measuring bending moment here. So it's 50 times 0 distance. So that is your bending moment at point A, 0. Then we are going to move the plane, that means our reference, to point B. So when we move our reference to point B here, you need to cover off this whole part here and looking at section which is towards the left only. We start from left hand. So you have 50 kilonewton multiplied by this length here, which is 0.1. That is your bending moment. Remember, bending moment is defined as force multiplied by length. So this length is 0.1. 50 times 0.1 about point B. Point B, we are at point B. From the force to point B is 0.1. Just now, from the force to point A, the distance is 0. Now, from the force to point B now is 0.1, and it is giving us a downwards bending. So that is why we have to consider a negative bending moment for this case. But since there's only one direction, we can put negative or we can omit the negative sign. So bending moment at point B, negative 50 times 0.1. So therefore, you have a bending moment of 5 kilonewton meter. Then the next, we move to point C. So when we move to point C, and the reference is at point C, okay, we have a force 50 multiplied by this length here, which is 1.5. 1.5. So you have 50 multiplied by 1.5, and then you have this 50 here multiplied by 1.4. So what you can do is you can take 50, which is negative, bending downwards, times with 1.5. Then plus, this one is acting up. That means it is causing the shaft to bend upwards alone. This one alone will cause the shaft to bend upwards. So that is why if you have a positive, you will have a positive 50 times 1.4 about point C. So that is what is written here. And the net would be negative 5 kilonewton meter. And as I have said, you can omit the sign here because there are only sign conventions showing you opposite directions, opposite phase, opposite direction. So we have only one, so that is only the negative. So you can ignore that. So bending moment at D, then you have 50 multiplied by 1.6, which is acting downwards. So that is why it's negative. And then you have this 50 multiplied by this 1.5, which causes the beam or the shaft to bend upwards. So that is why it's positive. Then, because we are taking a moment about this point here. So 50 multiplied by 0.1, and this one gives you a bending upward as well. So that is why it's positive. So the net bending moment at point E would be 0. It is always 0 if you were to consider that the shaft is under equilibrium, the state of equilibrium. Okay. Sorry for this. Okay, so what I can do is I will scroll everything out first. Okay, so the maximum bending moment we have determined or we have found will be 5 kilonewton meter. And when we take based on the strength relationship, there's only strength relationship. So the moment 5 kilonewton meter. Now what we don't have is the moment of inertia. So the moment of inertia for a solid shaft can be found by taking pi d4 over 64, and the y here, that is the vertical distance from the neutral axis, from the central axis. So in this case, for example, this circular cross section is a equilibrium section. So what happens is the neutral axis will cut through the CG of the section. So your x actually will be the neutral axis. So when the m is max, y must be max. When the sigma is max, when the sigma is max in the question, so do the y. The y must be maximum. So the outermost layer would be the maximum. So you measure from the neutral plane to this point here. So that would be equals to half diameter. Okay. So what we need to do is put everything together, okay, into the equation for I and for the Y. So we have something like that. So we can cancel out a d from here. So you have d cubed with this. So 64 becomes 32 when you cancel out with 2. So you have the sigma is equals to 32m over pi d cubed. Usually this is the formula that we use if we want to calculate the bending stress of shaft. Okay. So the objective is diameter of shaft. So you have to change this to the subject. So you have this, and then the whole thing cube root, you get a diameter of 0.0798 meter, which is also 79.8 millimeter. So you can round this up. Usually we have to round it up because, okay, when we go for a manufacturing process or when we go for a supplier, usually we show a complete figure, a whole number. Okay, so that is why we have to always round it up to a whole number. Like let's say, for example, 80 or 79. Even though if you've got 79.2, you still round it up to 80 millimeter. Or even you've got 79.1. Also, you will round it up to 80 millimeter. You will always round it up to something that is slightly larger, not smaller. If it is smaller, then it won't be able to withstand the stress. So that is why if you were, this is the exact value which we have got from the calculation. So that is why we have to round it up. Once we round it up, we have to round it up to a number which is larger than what we have found, so that it is able to withstand the stress which is given. In the questions I've already mentioned, we cannot design anything that will produce or that will give us stress which is greater than what is given. So if you use this number here, smaller number, let's say 78 or 79, 79, you put it into the diameter and you recalculate the stress. You will find out that the stress will be larger than what is not to be exceeded. Not to be exceeded. So remember, if you put this as 80 or 81 or 82 for the diameter of the shaft, you will get a value which is smaller, the bending stress which is smaller than what is given, which should not be exceeded. Okay, I hope this is helpful for your studies. Okay, and thank you. This is the end of the problem solving. We will proceed with the next one. Okay, thank you. Stay safe. Hello, welcome. Design of shaft again, but this time we will be dealing with the failure of shaft due to the combine of bending and twisting. So shaft subjected to combined twisting moment and bending moment. So the first thing we have is the maximum shear stress theory. This is one of the theory of failures. Okay, so sometimes we have to take based on theory of failures, in order to combine stresses. Because when you look into one component or one device or one component especially, there's not only one type of stress is acting on that particular component. There are various type of stresses. So in order to combine these stresses, combined stress, usually we apply this theory of failures. That is from my knowledge. Okay. So the first is the maximum shear stress theory, and it is given by this formula here. Usually you have plus and minus, but since we are looking at the maximum, so we only have half square root of the sigma here, which refers to bending stress, which is on the x-axis. If you have x and y axis together, then you have sigma x minus sigma y power 2. Okay, but then our case here is only on the x-axis. So that is the bending stress. Unless you have actual load, then that would be including the sigma y as well. Then this tau s here is the shear stress due to turning moment, due to torsion. Do you still remember the bending stress and the simple bending equation and the simple torsion equation? So in the simple torsion, you have a term which is the shear stress. And in your simple bending equation earlier, you have a term we call bending stress. So that is the bending stress, and this is the shear stress in torsion. Now, the second theory that we refer is called Rankin's theory. That is the maximum principal stress theory. So you have sigma max equals to half sigma b. Usually this here you have plus and minus, which give you sigma max and sigma min. For sigma max, usually is plus. For sigma minimum, which we are not looking at, is negative, minus here. So this sigma would be the bending stress. Okay, so if you refer to the original equation, this would be sigma x minus sigma y. And this also should be sigma x minus sigma y. So for our case, it's only bending stress. So that is why it is only sigma x here. That is the sigma b bending stress. And the tau is the shear stress, which is based on the simple torsion equation. So note, maximum shear stress theory, that is this, is usually applied for ductile materials such as mild steel, especially when we do design dealing with mild steel, which is ductile materials. Usually we design based on its maximum, on the maximum shear stress theory. Then for maximum normal stress theory, or the Rankin's theory, usually refers to brittle materials such as cast iron. Now, this part we're going to look into the simplification of the Rankin's theory and the maximum shear stress theory and the maximum principal stress theory. We're going to simplify it by putting in the sigma b and the tau, that is the shear stress. So based on maximum shear stress theory, the first, okay, we have this is the original formula. We know that bending stress based on bending, simple bending equation, strength relationship. We know that bending stress, previous video, 32 m over pi d cube. And then for shear stress due to torsion, that is based on simple torsion equation, based on strength relationship also as well, you got shear stress equals to 16t over pi d cube. The t is the turning moment and this m is the bending moment. The d would be the diameter of the shaft. So that means you're going to combine both of this, because when you refer to a shaft, when you have a pulley placed on a shaft, first the shaft will be subjected to bending, that is due to the weight of the pulley itself. Second thing is the shaft usually rotates, so that is why you have to consider torque due to torque or turning moment, and secondly due to bending moment. So your tau max, when you have substituted these two terms, these two equations here, you will get something like this. So you have 32 m over pi d cube, which is the bending stress, and then 16t over pi d cube, which is the shear stress due to torsion, due to bending. Simplifying this equation, that means extracting your 32 and this 4 becomes 2 power 2, so you have 32 power 2 actually, okay, when you include the 4 into the bracket. So it will become 2 times 16 power 2, okay, so it actually becomes 32. So this 32 you can extract out from this whole thing here, and then the pi d cube as well, because these are the commons, whatever mathematically you can see that whichever is common when you are simplifying, usually we extract it out. So what is left here is square root of this and this, the m square and the t square, where m is the maximum bending moment and t is the torque. That is based on maximum shear stress theory. Okay, that is for ductile materials. So, and we also know that, okay, based on shear stress, okay, a strength relationship, okay. So we can also say that it is equals to, okay, this side here is equals to m squared plus t squared square root, your pi d cube and 16 bring it over, pi d cube and 16 bring it over to the left hand side, you have pi d cube over 16 times tau max, and what is left behind is the square root of m squared plus t squared here. These are all mathematics. So if we take this term here to be equals to TE, this whole thing here to be equals to TE, then we have TE equals to this, and TE also can be equals to this. Okay, so TE, what is TE? TE is known as the equivalent twisting moment. Equivalent twisting moment. So now, when to apply this formula? That is only when the questions give you the value of shear stress, or if they ask you to consider, okay, the limiting condition of the shear stress. When shear stress is given in any problems or any questions, we can use or we can apply maximum shear stress theory and with these two formula to design the diameter of the shaft. I repeat once more, only when shear stress is given. And TE is called the equivalent twisting moment. So then the next would be the maximum principal stress theory. So which you have this, remember sigma B is 32m over pi d cube, tau is equals to 16t over pi d cube. Okay, substitute into the original equation of the Rankine's theory. So you will have something like that. Okay, simplifying it, you will get something like this. So actually this bracket here can be removed. Okay, so your pi d cube, sorry, from here, your pi d cube over 32 cannot remove, sorry. This plus should be removed. This 32 over pi d cube, this plus should be removed. 32 over pi d cube, bring it over. So you have pi over 32 times d cube sigma max. And this side, you have half m plus square root of m squared plus t squared. Remember, help me to remove this plus, yeah? So you have the equivalent bending moment as equals to this or this. And ME is called the equivalent bending moment. And when do we apply this? This is only when the problems or the questions give you, okay, the maximum bending stress. Then most of the time they give you in terms of direct stresses like tensile or compressive, okay? Or most of the time they will only give you, okay, the direct stress is that much, but that is understood that you will be referring to the maximum bending stress or the tensile and compressive. Okay, so ME is known as the equivalent bending moment. Okay, that's for this part. Okay, the theory for the combined bending and twisting. See you, stay safe. Okay, problem solving due to combined bending and twisting. This will be the first example. Okay, so in the example 7, actually is 7 now. Example number 7, a shaft made of mild steel is required to transmit 100 kilowatt at 300 RPM revolutions per minute. The supported length of the shaft is 3 meters. So this length of the shaft is 3 meters long. It carries 2 pulleys, each weighing 1,500 Newton. So 1,500 and 1,500. At a distance of 1 meter from each end respectively. So this from the left hand end 1 meter, this from the end 1 meter. Now, assuming the safe value of shear stress should be 60 MPa, and find the diameter of the shaft. So in this case, they have only given us the shear stress. So if let's say we work based on shear stress, then okay, what we need, when you look at TE, the equivalent twisting moment for shear stress only. ME is only for bending stress or for direct stress only. So TE, you have square root of M squared plus T squared. Look at this first. Don't look at the rest of the things first. M is the maximum bending moment. M is the maximum bending moment. So the first thing we have to calculate the maximum bending moment. So what we need to do is consider a reference plane starting from left-hand end again. So you ignore or omit everything here. When you refer to the reference plane, which we are placing it A, only refers to everything towards the right. So you have the reference plane here, my pointer. So you have the force 1500 multiplied by distance. The distance of this point here, my pointer, from the force is 0. So you have 1500 multiplied by 0. So that is why it's 0. So then you move the reference to point B. Then you have this 1005 times 1 meter to the point I place here, my pointer. Okay, 1005 times 1 meter causing bending upwards. So you have 1005 times 1, which is positive. Then after that, okay, but for A, this, okay, 1005 times 1 here. But for this 1005, distance here from this force to this point is 0. So that's why this one is omitted. Then from point C, for point C, the pointer at point C, then you have 1005 times, I think this is 2 meter. Okay, then you have this 1005 times 1 meter. So this 1005 times 2 meter actually causing the shaft to bend upwards. Alone, this one alone will cause the shaft to bend upwards. If you were to refer to this alone, this will cause bending downwards about point C. So that is why this is positive and this is negative. So it will give you a net bending moment of 1500. When you consider at point D, that means towards the end of the shaft, usually it's 0. You don't need to calculate. You just put 0. Because for the equilibrium of the shaft, usually at the last point of the supporter, the support is at the end of the shaft. If the support only at the end of the shaft, then the bending moment is 0. So from this, you can plot your bending moment diagram. So the maximum bending moment is 1500. So that is how I got my maximum bending moment, 1500. Okay. So and then the next thing, what about the T? The T can be found by referring to the power and the speed. The power and the speed. So you use power is equal to 2 pi nt over 60. Okay, so you can use power is equal to 2 pi nt over 60. So from this we can find out the torque. 60 times power over 2 pi n. So it should be Newton meter, which is 3183. This should be 3183. So place it here. So for completing this, you have 3519 Newton meter of torque. Then again refers to TE, but this time is equals to pi over 16 times d cube times the tau max. Our objective is to find out the diameter of the shaft. So that would be our subject. So d cube, manipulating this, and then cube root the whole thing, you get the diameter of 66.8 millimeter. Remember what I said, you can only round it up to a larger figure, not a smaller figure. Okay, so you can round it up, become 70 millimeter or 68 millimeter or 67 millimeter. But never to round this up to 66 or 65. Even though if 66.1, you still round it up to larger, 70, 67, or 68. Never to bring it down to 66 if it is 66.1. Okay, thank you for your presence. in this class. Thank you very much. Stay safe. Bye. And see you all for the second example, which is example 8. Now, a solid circular shaft subjected to a bending moment of 3,000 Newton meter and a torque of 10,000 Newton meter. So in this question, they've given you both the bending moment and the torque. The shaft is made up of this material, okay, steel. Okay, the name of the steel in the grade is 45C8. Okay, steel having ultimate tensile stress. Now, whenever you see this, you must have a factor of safety. And the ultimate shear stress is 500. So they have given you both. So you have to use both the ME for this, ME, and this TE to design the shaft. Assuming a factor of safety of 6, determine the diameter of the shaft. So your objective is to find out the diameter of the shaft. So this would be the shaft subjected to bending. So for allowable bending stress, you have to take the ultimate tensile stress 700 divided by 6, which is the factor of safety. So this would be the allowable value. This is the value that it is allowed to use for the design. You cannot use ultimate, remember. Okay, so for shear stress, the same thing divided by the factor of safety. So you have 500 divided by 6, so you have 83.3. So based on equivalent distinct moment first, shear stress and tensile stress both are given, so you have to consider TE and ME. So both M and T are given, we can just straight away substitute, find out the TE. So based on the TE, you can design the shaft diameter. So the shaft diameter, D cube is the objective, or the subject. So you have this. So cube root, you get 86.1 millimeter. That is the first value. Then the next, based on equivalent bending moment, you have the equivalent bending moment is equal to this. So put in the value of M and T, so you will be able to find out your ME here. So 6.72, and take this ME for the shaft design, okay, to find out the diameter of the shaft. So you use this formula here with the allowable value here, 116.7, not the ultimate, okay. So cube root, you get 83.7. So from this, you compare. Which one is larger? This one. So this would be the safe value. This will not. Because if you put this to design the shear stress, it fails. Okay, so that means if you take this value, put it here, take this to be your object or subject, find out the shear stress, you will know, you get to know that the shear stress will be greater than this value. So it will directly fail. It will definitely fail. So if you take diameter 86.1, okay, then you put it here, then find out the direct stress here, will definitely give you something lower than 7. Sorry, something definitely lower than 6.7. So this value will be safe, this value no. So our answer will be 86.1. So taking the larger of the two values, that is 86.1. Please remember, this one you need to round it up to 87 or 88 or 90, not to 86 or 80. Even 85, 84, everything smaller than the value cannot. When you round it up, it must be larger. That's my final advice. Thank you. Thank you very much. Stay safe. Bye-bye. And see you all in the next session. Bye.